All right, guys, hi. So today's lesson is all about roots and zeros. And remember, roots or zeros are the solutions to a function, or where the graph of a function intersects the x-axis. So we're going to be able to determine the number and types of roots for a polynomial function, and then we'll be working on finding the zeros of a polynomial function. All right, so as we begin here, we're going to talk about the fundamental theorem of algebra. So every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers, real or imaginary. So that's what we consider complex, is it can be real or imaginary. So I'm going to ask you guys to do these 4 problems. They start off kind of easy and then they get a little harder. And all of these problems you've seen something very similar to before. So solve each equation and then state the number and type of roots. So if there's 2 real roots, or 3 roots, 1 real, 2 imaginary complex, okay? So go ahead and pause and do your best, and then we'll talk about them. Okay, so the first equation, a minus 10 equals 0. Pretty easy here. Solving for a, add 10 over. A equals 10. And we have 1 real root. That's it. 1 real root. That's all you're being asked to do. All right. That is a linear equation, if you remember that. So you'll see a pattern emerging here. So number 2, x squared plus 2x minus 48, should seem extremely familiar from the last chapter. It's quadratic, and I like to try to factor first if I can. If I can't, then I would use completing the square or a quadratic formula. But this looks factorable to me because the factors of negative 48 that would add to 2 would be positive 8 and negative 6. So x plus 8, x minus 6 are the 2 factors here. And if we solve using the zero product property, I'll just be kind of quick about this, x would be negative 8 and positive 6. So we have 2 real roots. So we're checking our answers here. 2 real roots. Notice that this one was quadratic. So the first one was a degree of 1. The second one has a degree of 2. All right, are you catching on to the pattern? So the next one has a degree of 3. And always remember, try to factor out the greatest common factor. So in this case, I see between 3 and 18, we have a common factor of 3, and between x cubed and x, we have a common factor of x. So if I factor out 3x, I'm going to have x squared plus 6. And now I can use the zero product property. That quadratic in the parentheses is not factorable, but if we set equal to 0, we can solve for x. So I have 3x equals 0, and I have x squared plus 6 equals 0. Don't have a lot of space here, but if I divide by 3, x is 0. And I subtract 6 over, I'm going to have x squared equals negative 6. And I've isolated my x, so I just need to take the square root. Don't forget plus and minus. So x equals, that's imaginary, plus and minus I root 6. And so for this one, I have, here are the answers, 0 and plus and minus I root 6. I have 1 real and 2 imaginary, and that's a cubic function. All right. And then finally, I have this over, y to the 4th minus 16. Okay, that's a difference of squares, so you can factor that. I'll use different colors so you can see a little better. That's factorable because these are both perfect squares. So y squared plus 4 and y squared minus 4. And then I notice that the y squared minus 4 is also a difference of squares. So the first factor of y squared plus 4 is not factorable, but this factor is y plus 2 and y minus 2. Oops, equals 0. And now we can set all 3 factors equal to 0 and solve using the zero product property. And fortunately, I just don't have a lot of space here. So I have the y squared plus 4, the other two factors of y plus 2 and y minus 2, that just equals, so y is plus or minus 2 there, okay? The y squared plus 4, I'll go up here. Y squared plus 4 equals 0, so y squared equals negative 4. It's kind of like just similar to the one we just did previous. So we take the square root and plus or minus, and so y equals plus or minus, that's a perfect square of 2i. All right, so we have, in this case, we have y equals plus or minus 2, which is right here, and we have plus or minus 2i, which is up here. So we have 2 real and 2 imaginary roots. And so notice that the degree, the first one has a degree of 1, we had 1 root. The second one was a degree of 2, we have 2 roots. The third was a degree of 3, we have 3 roots. And the fourth one was a degree of 4, and there are 4 roots in the complex number system. And so that's what you're supposed to be recognizing, is that pattern. All right, so that's kind of an important pattern because we're going to be solving polynomials that have higher degrees now. Descartes' rule of signs is a rule that allows us to know how many positive and negative real roots we can possibly have for a polynomial. So the rule goes like this. So the number of positive real roots for p of positive x is the same as the number of sign changes of the coefficients of the polynomial's terms, or less than this by an even number. So that's kind of weird, but if there are 4 sign changes of a function, then there could also be 2, because we're going down by an even number, which is 2, or there could be 0. So there could be 4, 2, or 0 positive real roots, okay? What if there were 5 sign changes? Again, we go down by an even number, so that would be 3 or 1. There can't be a negative amount of anything, so 1, there would be 1 total. So it just gives you a possibility of how many positive real roots. And then the number of negative real roots for p of negative x is the same as the number of sign changes of the coefficients of the polynomial's terms, or less than this by an even number. But for p of negative x, we change the sign of every odd degree term, because if you put a negative number and raise to in for x, a negative x in, a negative value in, and raise to an odd degree, you'll remember that whatever to that power would be a negative value, right? If it's an even degree and we put a negative number in, a negative to an even degree will be positive. So that's why we only change the sign for the odd degree terms. So the example, p of x is a function. It's negative x to the 6 plus 4x cubed minus 2x squared plus x, or excuse me, minus x minus 1. So that's p of positive x here. So the sign changes are negative to positive. That's a sign change. That's why I put a yes right there. So negative to positive, there's a sign change. And then positive to negative, there's another sign change. Negative to negative, no sign change. Negative to negative, no sign changes. So there's 1, 2 sign changes. So the number of positive real roots would be 2 or less than this by an even number, 0. So we have 2 or 0 positive roots. So p of positive x, we would have 2 or 0 positive real roots. Now, for p of negative x here, every odd degree term, the sign changes. So up here, this is an odd degree term, and this is an odd degree term. So we change those signs. So this positive 4x cubed would become negative 4x cubed, and this negative x would become positive x. So down here, p of negative x is negative x to the 6 minus 4x cubed minus 2x squared plus x minus 1. So from here, from negative x to the 6 to negative 4x cubed, negative to negative, there's no sign change. Negative to negative, no sign change. Negative to positive, there's a sign change. Positive to negative, there's a sign change. So there's also 2 or 0. Here we go, sorry. 2 or 0 negative real roots. So if I'm making a chart, and you're not expected to do this, but it's helpful for me, the number of real roots, I should say, is number of, well, I don't want to say real because there's imaginary in there too. The total number of roots has to be 6 because it's a 6-degree polynomial function. So I know I have, for positive roots here, I have 2 or 0. So I just made a little chart of if I have 2 positive, I also have 2 or 0 negative, and 2 plus 2 is 4, so that means I'd have to have 2 imaginary to make a total of 6 roots, okay? If I have in this second column, or second row, I guess I should say, if I have 2 positive and no negative, then I have to have 4 imaginary to make a total of 6. And then finally, if I have 0 positive, 2 negative, I'd have to have 4 imaginary. And then 0 positive, 0 negative, all imaginary. So it just helps you know the different combinations of what could happen for this particular function. So now we're going to practice Descartes' rule of signs. It's a pretty easy little rule once you get the hang of it. Okay, so state the number of positive real, negative real, and imaginary zeros of each function. So we'll start with p of positive x. And what I do is I just write out the signs. So the first sign is positive, the second sign is negative, the third is positive, and the fourth is positive, all right? So how many sign changes are there? We have a sign change here. So there's 1. We have 1 here, and then there's not 1 there, so it's a no. I just write yes, yes, no. So for a p of positive x, we have 2. So for p of positive x, we have 2 or 0. Positive real. All right, 2 or 0. Now for p of negative x, for every odd degree term, so here and here, we change the signs. So that was a positive x cubed, so that's going to be negative now. The negative 5x squared, we keep it negative. The positive 2x becomes negative, and the positive 4 just stays positive, okay? So now, how many sign changes are there? That's not a sign change. This is not a sign change, but this is. So we have exactly one negative real. All right? So because this is a 3rd degree polynomial function, there has to be 3 roots total. So we have 3 total roots. And that is positive and negative real and complex. So we could have 2 or 0 positive, 1 negative, and then if we have to have 1 negative for sure, right? So if we have 1 negative and 2 positive, we have no complex. But if we have 1 negative and 0 positive, we would have 2 complex or 0. So 2 or 0 complex or imaginary, I guess I should say. So that's how you work on that. So if you want to give this number 2 a try, even though it doesn't say your turn, go ahead and try it. That would be great. So go ahead and pause and give it a shot. Okay, so this is a 4th degree polynomial function, so that means there's going to be 4 total roots. And so if we're looking at the p of the positive reals, we've got a positive, a negative, a positive, a positive, and a negative. So how many sign changes are there? There's 1, 2, 3. So that means for positive real, we have 3 or 1. All right? For p of negative x, we change the odd degree terms only. So this is odd and this is odd, right? So we start off with positive and then we change that to a positive. This is positive, that changes to negative and negative. So how many sign changes do we have? We have 1 here and that's it. So for negative roots, for negative real, we have exactly 1. So if we have 4 total roots, we could have 0, right? Complex. We could have 0, or we could have 2, because there's 1 positive and 1 negative. So we'd have 2 or 0, complex roots. Okay, so you'll work on that part. That's one of your objectives today, is just to practice Descartes' rule of signs and be able to state the number of positive real, negative real, and imaginary zeros, okay? The next part of this lesson is we're going to be working on the complex conjugates theorem. So remember, a conjugate of a complex number is the opposite sign. So if a plus bi is a complex number, the conjugate of that is a minus bi. So if a, and conjugates, I know I've said this in the past to my classes, complex roots always come in pairs. And so its conjugate of a complex root is always a root itself. So that's what this complex conjugates theorem states. If a plus bi is a 0 of a polynomial function, then so is its conjugate a minus bi. So what you're going to be doing is going backwards. Given the roots of a function, write the polynomial that has those roots. Now you've done this with quadratics, and now we're just taking it a step further, because we've always been given real roots. Now we have imaginary or complex roots, okay? So we have, write the polynomial function that has the given roots 3 and 2 minus I. Well, 3 is a real root. However, 2 minus I is a complex root, and so we need to apply the complex conjugates theorem and know that its conjugate is also a root. So the conjugate of 2 minus I is 2 plus I. So that's using the complex conjugates theorem. All right? It's almost like writing a proof, kind of like an algebraic proof. I'm stating what I'm using to be able to make that statement. So now we take the roots and we plug them back into their factored form. So if we have plus 3, then remember their factored form would be x minus 3. And you probably remember that from the last chapter or so. And then the 2 roots of 2 minus I and 2 plus I also go back into factored form, but we separate them off with these brackets to separate them from the real root. So I have x minus 2 minus I and x minus 2 plus I. Now that looks a little scary. So what's going to happen is we're going to do a little regrouping, okay? So we're going to regroup. Regroup the terms by moving the parentheses over to the left one on each of these complex roots. So notice the parentheses just shifted over to the x minus 2. And these parentheses also shifted over to go around x minus 2. However, this negative was distributed here, and that's why we have a positive here, okay? So we just distributed the negative and regrouped. Distribute the negative here, and that's why that's now negative. That's a little tricky, but if you just remember you have a plus and minus I, then that's always going to be true. It's always the same process, okay? Now we just rearrange and rewrite as a difference of squares. We have the x minus 2 times x minus 2, and then positive I times negative I is negative I squared. And so now we'll use FOIL. So x minus 2 times x minus 2 is x squared minus 4x plus 4. And then remember that I squared is negative 1. And so negative times negative 1 is positive 1 right here. So we're foiling and replacing I squared with negative 1. And then we will simplify what's in the brackets there. So we have the x squared minus 4x plus 5. And now we basically just have a trinomial times a binomial. And you'll use the distributive property to multiply the binomial times the trinomial. This is not anything you've never done before. It's just multiplication of polynomials. So use the distributive property, distribute x to x squared, and you get x cubed. X to negative 4x, you get negative 4x squared. X to 5 is 5x. And then negative 3 to x squared is negative 3x squared. Negative 3 times negative 4x is positive 12x. And negative 3 times 5 is negative 15. And then we just simplify. And I did forget to rewrite that this should say f of x equals, sorry, I forgot to drop that down. So f of x is x cubed minus 7x squared plus 17x minus 15. That is the function that has the given roots of 3 and 2 minus I. It gets a little faster, trust me, I'm sorry. I know that was kind of a lot. So let's go through. I wanted to swap these, but I'm not able to do that. So let's do number 2, and then I will have, number 1 can be a your turn, okay? So let's try that. We'll do your turn on that one. So number 2, we'll drop down here. So this one's a little tricky because we have 3 given roots, 2i, 5, and negative 1. Now 5 and negative 1, those are real, okay? So we have x, oops, hang on, sorry. Let me just erase that. I have to try to write small because this will get lengthy if not. So I have f of x equals x minus 5 and x plus 1 for the 2 real roots. And then the 2i, don't forget we have negative 2i using the complex conjugate theorem. So I'm going to put those in the brackets here. So that's x minus 2i and x minus negative 2i, which would be x plus 2i. So I'm just going to separate those because I want to multiply those separately, okay? So you can always multiply two expressions together, but not more than 2. So I can multiply x minus 5 by x plus 1, and that's going to give me the x squared plus x minus 5x minus 5. All right, I'll just separate with parentheses. And then that simplifies to x squared minus 4x minus 5 so far. All right, and then over here, if I multiply x minus 2i times x plus 2i, I've got x squared plus 2xi minus 2xi minus 4i squared. And then these guys cancel out, right? And then don't forget this I squared is negative 1. So now I have x squared, negative 4 times negative 1 is positive 4. And now I have a trinomial times a binomial, and I can use the distributive property. And if I do so, I'm going to have x to the 4th plus 4x squared minus 4x cubed minus 16x minus 5x squared minus 20. So just using the distributive property. And then finally, make sure you write, f of x equals, I'm just trying to get a little space there. So your function comes down here. I typically forget to write that. F of x is equal to, adding like terms, x to the 4th minus 4x cubed minus x squared minus 16x minus 20. So we went from 4 roots, so just a reminder of putting all these pieces together. We were given 3 roots, but we used the complex conjugates theorem and to know we have actually 4 roots. We have a 4th degree polynomial function. So yeah, we have 2 real and 2 imaginary roots. So the last example I would like you guys to do on your own. So the roots are negative 4 and 3 plus I. Go for it. Okay, so we have the 1 real and the 1 complex. So that means you're using the complex conjugates theorem, and we'd also have 3 minus I as a root. So we have f of x is equal to, the first root is the real one, so that'd be x plus 4. And then in brackets here, I'm going to have the x minus 3 plus I. Parentheses around this. There we go. And another set of parentheses, x minus 3. Oops. I need to erase that. There we go. 3 minus I. Okay, so now we're just going to distribute the negative to 3 plus I and negative to 3 minus I and regroup. So this is going to become x minus 3 minus I back. I always forget my double parentheses. And then this is going to become x minus 3 and then plus I. And then we can keep going. I always rewrite the x plus 4. I tend to forget that because that's still a factor out there. And now, again, we're going to rearrange. So we have x minus 3 times x minus 3, and then negative I times positive I is negative I squared. So it should get a little faster. And then we're going to use FOIL here. So that's x squared minus 6x plus 9. And then remember, that's going to be negative 1. So that's going to be plus 1. Oh, and then, x squared minus 6x plus 10. There we go. And then we have our x plus 4 factor. And then we just need to use the distributive property. And so I'll have to do it over here. So now I have f of x equals, you distribute the x plus 4 in there, x to the third minus 6x squared plus 10x plus 4x squared minus 24x plus 40. And then simplify one more time. F of x equals x to the third minus 2x squared minus 14x plus 40. Woo. So it's a third degree polynomial function. We have 3 roots, 1 real, 2 imaginary. All right, guys, you've got quite a few good examples in your notes. I know sometimes this is tricky, so you'll need to look back at those as you're working on your homework assignment. So make sure you do so that when you come to the problems like this, that you have something to look at and remember how to set these problems up. Okay, thank you.